Right, so we're going to start rigid body motion. So rigid body motion is a very specific case of motion. So far we've looked at general motion, i.e. how an object moves or how some chunk of mass moves when there's a force applied to it. But a special case of this is what happens when you have a whole bunch of objects that are attached together in a sense, and they move in a coordinated way, i.e. rotation. So let me define what a rigid body is. A rigid body is an extended object, meaning not just a point mass, that rotates as one. And none of the parts move relative to each other. Hold on, it's hard to talk and write at the same time. None of the parts move relative to each other except the motion due to the rotation. And I'll be more specific in a sec. So what I mean by that is, let's say that instead of just having a point mass that just moves, or a collection of point masses that can move independently of each other, we instead have basically what amounts to like a physically real object. Like think a baseball bat, or I'm just going to draw this lump of stuff. Imagine we had this lump thing, and we punched a hole through it and stuck a rod through that hole. Then this lump thing, I'm going to try to draw it again, could rotate about that rod. And so the point is that even though these points, if we have 2 points, say point A and point B, even though those points are technically moving relative to each other, A and B, because, you know, initially B was directly to the right and now B is directly to the right and up, even though they are moving relative to each other, all of that motion is encapsulated by the rotation. So we can be more precise with this. So let's say that this angle here is theta. Then A will travel, say, this distance, call it SA, and B will travel this distance. It's a terrible straight line. Call it SB. S stands for arc length for some reason. So let's ask, what are the motions of A and B? How do A and B move? Because you could have imagined that these are just a whole bunch of particles that interact with each other, but you could treat them as, you could treat A as its own system or B as its own system, and then they just interact with each other in some way, right? All a solid object is a whole bunch of atoms and molecules glued together by various forces. So what we mean when we say a rigid body is that those forces keep the relative arrangement of its components intact. So like, for example, this part will always be close to this part, regardless of how it's rotating or how it's moving. That's what makes a rigid body rigid. Right, so let's answer, how do A and B move? Well, the arc length, SA, that's just equal to the radius, the distance from the axis of rotation to the point A, times the angle theta. That's just an arc length formula. Similarly, the arc length for B is RB times theta. And so we can figure out the velocity. The velocity, it's just the, sorry, this is the speed, not velocity. The speed is just the distance traveled, the time derivative of the distance traveled. And similarly, we can do the same for point B, time derivative of the distance traveled. Now, we have a formula for SA and SB, right? So we can substitute that in. That's d dt of RA of theta times theta, d dt of RB times theta. And notice that the distance, that when the object is rotating, the distance doesn't change, this RA and RB, those are fixed. The only thing that changes is the angle. So this becomes RA times d theta dt. This is RB times d theta dt. And so we just call d theta dt, we give this a name, we call it omega. It is the angular speed. Or once eventually we'll call it the angular velocity because it is indeed a vector. So this is just RA times omega. This is RB times omega. So as you can see, even though they're moving at different speeds, and even though they're moving relative to one another, they still have this feature in common where the speed that they're moving at is just proportional to an angular speed, which doesn't care about where you are on the object, and the distance that the point you're interested in is from the axis of rotation. So this omega, which is the angular velocity, or it's the angular speed in this case, because we're in one dimension. This angular velocity is the thing that joins objects that are rotating, or that joins objects on a rigid body. If they have the same omega, they could very well be part of the same rigid body if two points have the same omega. So when we talk about rotation, which is what we're going to do, is the direction of angular velocity expressed as clockwise or counterclockwise, or is expressed in terms of all three? Good question. We will get to that. In a sense, it will be expressed as clockwise or counterclockwise relative to a certain axis. So I will get to that, but we're not there yet. But good question. Right. So we only talk about the angular motion when we talk about rotation. It's not very useful to say that that point A on that object is moving at 5 meters per second. It's more useful to say the whole object is rotating at 2 radians per second, right? Because then you can describe the speed of any point on your object just by knowing its distance from the axis of rotation and the angular velocity. So I'm going to give you the set of variables that we use to describe rotation or rotational motion. So we have rotational position, which is just theta as a function of t. Think x of t. That is the standard translational position. We just called it x of t for position. There's displacement, which, just like how we had delta x as the displacement, the distance between 2 points, we have angular displacement. This is delta theta, which is just, say, theta 2 minus theta 1. There's average, oh no, what happened? I think I know what's happening. I think my hand is clicking something at the bottom. Come on, zoom out just a smidge. Or don't. This'll do. There's average velocity, just like before. So all of these things that we talked about before have a rotational equivalent. So that would be omega average. By the way, this omega, it's not a W, it's like a curly W. And it's the Greek letter that makes an O sound. So this omega average is just delta theta. It's just the displacement over time, just like how V average was delta X over delta T. Then we have instantaneous velocity. Just the same. It's just the time derivative of the position. This is omega of t, which is d theta dt. We have the average acceleration. Just the same. We give for acceleration, we use the symbol alpha, Greek letter A. It looks like a little fish. And that's the change in speed, or change in angular speed over time. And then we have the instantaneous acceleration. These are, and you could put in a rotational in front of all of these words and it would be more explicit. So we have alpha of t equals d omega dt. So everything goes as before. All of these definitions are the same. It's just, instead of talking about an object moving from left to right, we're instead talking about an object rotating from point A to point B. And maybe its acceleration, maybe its rotational velocity increases, so it starts off slow and then it ramps up. Or what have you. You can do all of the same things that we've done, just reframing things instead of moving linearly, think rotating in a circular manner. And so just like how we went from a constant acceleration to get a kinematic equation for linear motion, if we have constant acceleration, let me just jot this down. This implies that x of t is x naught plus v naught t plus 1/2 at squared. We can do the exact same thing for angular motion, right? So if we have a constant, not accelerational, if we have a constant angular acceleration, then we get the same type of kinematic equations, but talking about rotation. We have theta of t is equal to theta naught plus, let's say, omega naught times t plus 1/2 alpha t squared. And then we have omega of t is omega naught plus alpha t. And then you can rearrange these in the same way as we did before. You can get things like, you can derive other expressions like the final rotational velocity minus the initial rotational velocity squared is equal to twice the acceleration, rotational acceleration, times the initial angle, or the final angle minus the initial angle. You can do a whole bunch of things, but all we're doing is we're basically just relabeling things. Like all of the equations that you saw before, you can relabel them and they apply equally well for rotation. And the reason for that is because all of the business that we talked about at the beginning of the course, this constant acceleration business, those are just facts that come from integrating things. Those are just mathematical facts. So as long as we can talk about these quantities in the same way, as long as it makes sense to talk about an angular position, an angular velocity, and angular acceleration, then you can relate them in much the same way. And as long as your angular acceleration is constant, all of the math we did is still valid. So the only difference between what we did before and what we do here is that distance, let me jot this down. The difference here is that quote unquote distance, this theta, is measured in radians, not meters. And importantly, it's not measured in degrees either, even though you could convert it to degrees, just because radians is the natural unit for rotational motion. So stick to that. So like, for example, the you would plug in at 5 radians for theta naught, if that's the initial angle that something is at. Then you would plug in 2 radians per second for omega naught, if that's the initial angular velocity it has. And you'd plug in, I don't know, 0.1 radians per second squared, if that is your constant acceleration. And then you would plug in and you would solve and the units work out, and you would say that at t equals 19, the object's rotational position, i.e. how far it has rotated beyond its 0 point, is 78 radians or something. Now, importantly, just like how in the one-dimensional case, you would have to fix a place, like a reference point. You'd have to say, okay, at this place, x equals 0. So if I go that way, that's x equals 2, and and then if I go that way, x equals minus 2. Just like how you have to fix a reference place for position, for linear motion, you have to do the same thing for rotational motion. You have to say, where is the angle equal to 0? So maybe, like, for example, maybe you have a rod that's rotating on one end. Maybe we call this line here theta equals 0, and then theta increases as it rotates. Then you have a reference point, and so now it makes sense to say that the angle that it's at is 78 radians or something. So you have to be a little bit careful here. It can get a little bit confusing, but just keep in mind what we're going to do is super, super analogous to everything that you've seen before and things that you're comfortable with, I hope anyway. Just an aside, a quick note, and this is important, centripetal acceleration has nothing to do with alpha, or has almost nothing to do. Like they're not the same thing by any stretch of the imagination. They don't point in the same directions, all of that business. So just keep that in mind. So there, Raul asked a good question. This is about the direction of rotational motion. So let me talk about that for just a minute. So, so far I've only talked about 2D rotation, i.e. rotation in a plane. And in that case, you can just say positive or negative would imply clockwise or counterclockwise, or positive would be counterclockwise, negative would be clockwise. And that's just like how in one-dimensional linear motion, if you're only working in one dimension, you can just say positive means right and negative means left, and you don't have to worry about vectors. However, once you go to three-dimensional linear motion, this is motion that could be in any which way, translational motion, then you have to introduce vectors, and we have to do the same thing here. Because a physical three-dimensional object could rotate in a whole bunch of different ways, you need to actually introduce the notion of vectors to talk about the way in which it's rotating, about what axis is it rotating. So the way that we extend rotational motion to 3D is we use the right-hand rule. So the right-hand rule pops up a lot. Remember, I mentioned that this would come up when we talked about the cross product. But the basic idea is if you curl your right hand in the direction that the object is rotating, so let's say that this object is rotating like this, right? Then I would take my hand, I would curl it in that direction, then your thumb points in the direction of the vector that describes the velocity vector, for example. So let me just write down an example here. Let's say that we have x is this way, y is this way, and then z is out of the paper. So if an object, let's say we just have an object that's, let's draw a better object, something lumpy. Let's say that this is rotating this way. Well, then I would use my right-hand rule, and I would say that the direction vector for its rotation points out of the paper, points in the z direction. So I might say that in this case, omega is, and let's say it rotates at, say, 2 radians per second, right? For example. Then I would say omega is 2 radians per second in the k hat direction, because the direction vector associated with that rotation is in the z direction. And the reason why we use the right-hand rule is basically just because we want some way to specify, is it clockwise or counterclockwise relative to some axis. And the right-hand rule gives us a convenient axis to use to describe counterclockwise motion. So like, if the rotation is in the xy plane, then the right-hand rule will always tell you if it's positive in the z direction, then it's counterclockwise in the xy plane. And you can make this whole argument with z or x or whatever. So it's just the choice that we make. You could have used the left-hand rule, but for convention's sake and for consistency, we use the right-hand rule. Would you have to mention your reference axis for theta? Right, so just as the omega would be a vector, you would talk about a displacement using the right-hand rule. If it's gone 5 radians counterclockwise in the xy plane, then delta theta would be 5 radians in the k hat direction. So the object is not moving forward in the k direction. It's just rotating in the xy plane. And that's an important point to make. When I say that a rotational vector, or a vector like omega, points in a direction, that doesn't mean there's motion in that direction. So remember that I said a vector is not an arrow. A vector is just a mathematical representation of something. So when we're talking about rotational motion, what it's representing is it's representing a rotation in a plane perpendicular to the direction it points. So Raul, would you have to mention your reference axis for theta? Usually the reference axis is just defined to be the x-axis in this case. But yeah, I mean, in general, you would have to. So if you turned it counterclockwise, it would be minus 2k. Yes, if you turned it clockwise, it would be, the vector would point in the positive, or in the negative k direction with magnitude 2 radians per second, precisely. And if it were, so now let's say that it rotated like this way, right? Like into and out of the board. So it's rotating in the XZ plane. Well, then we would say that omega, well, what's the right-hand rule? So it would go into the paper. It would go into and out of the paper. So I would use my right-hand rule, and my thumb points in the Y direction. So in that case, if this was, say, 3 radians per second in that direction, actually, let's combine both of these. Then it would be 2 radians per second in the k-hat direction and 3 radians per second in the j-hat direction. And so you could have, so this would combine to say that it's rotating a little bit this way, rotating a little bit this way, and it would have a more complicated rotation. But the whole point is we can break down the rotational, or we can break down the rotational motion into vectors just by looking at what direction is the rotation perpendicular to. Right, so there will be a lot of practice on this, and office hours are going to be a good time to go over more of these things, but I hope that was helpful. So we're going to continue. So it's not just enough to talk about rotational kinematics, right? Like, just like it wasn't enough to talk about linear kinematics or translational kinematics, we had to talk about force, we had to talk about energy and momentum. We're going to skip over the rotational equivalent of force for now. That'll come Friday, because it does get tricky. Instead, we're gonna jump to energy. So, so the question is there an equivalent to kinetic energy and momentum for rotation? Right, and so perhaps you already have an inkling that that's true, right? I mean, first of all, we saw that there was an equivalent for position, velocity, and acceleration in rotation. There's a correspondence between linear motion and rotational motion. But further, you might have the intuition that a thing that's really heavy, if it's rotating really quickly, is hard to stop. And so that's at least something like momentum, just like how a truck that's barreling towards you is hard to stop because it's really heavy and it's moving really fast. So you might already have this intuition that there is some sort of equivalent, something equivalent to kinetic energy and momentum, but for rotational motion, and you'd be right. So let's first talk about kinetic energy, the kinetic energy equivalent for rotation. Obviously, the answer is yes, it does exist. So let's just look at an example. Let's say that we have a rod. And by the way, we're going to use rods a lot. That's a pretty common strategy. Let's say it's rotating about this axis here. And let's just look at a whole bunch of different points on that rod. Or let's break it up into chunks. Right, so maybe this is chunk 1, this is chunk 2, this is chunk 3, this is chunk 4, this is chunk 5. So as it's rotating, this chunk will move that way, this chunk will move that way, this chunk will move that way, and so on, right? And so we can find the total kinetic energy of the system just by examining the kinetic energy of each of the parts and adding them up. So this would be 1/2 m1, let's label this 1, 2, 3, 4, and 5, m1 v1 squared, plus 1/2 m2 v2 squared, plus 1/2 m3 v3 squared, and so on, right? Up there'd be five terms, and each of them would have different speeds because the chunk 5 is moving faster than chunk 1. So the speeds, we can find that the speed of a chunk is proportional or is equal to the distance that it is from the axis of rotation and the angular velocity. So this is r is distance from the axis, and omega is this is the same for every chunk, right? Because the whole object has some rotational velocity. It's not like that one part of the object is rotating faster than another. They cover the same amount of angle in the same amount of time. So that means that the kinetic energy for a rod is 1/2 m1 r1 squared omega squared plus 1/2 m2 r2 squared omega squared plus ... All of those omegas are the same, by the way. And so we can factor this. This becomes 1/2 m1 r1 squared plus m2 r2 squared plus ... times omega squared. And so what we've done now is if we call this thing, we call it something new, let's call it I. This has the name rotational inertia. Remember that inertia was basically mass, also known as the moment of inertia. Moment of inertia is just an older term for it. And I'll use them interchangeably. If we call that thing I, then our formula looks like kinetic energy of the rod equals 1/2 I omega squared. And so what you can see here is that we have another correspondence with linear motion, right? The kinetic energy for linear motion, I'll just call it translational. This is 1/2 mv squared. We already know that omega is the rotational equivalent of v, right? Angular velocity versus translational velocity. And it looks like this I plays the role of mass. And indeed, the name should make that obvious, that it's rotational inertia. It's the inertia associated with speeding up or slowing down something in a rotational manner rather than in a translational manner. And so there is this correspondence that we now have. We have that 1/2 mv squared corresponds with 1/2 I omega squared. And we have that m corresponds with I. We also have that x, the vector x, or let's say the vector r, corresponds with the vector theta. The vector v corresponds with the vector omega. And the vector a corresponds with the vector alpha. So we have this correspondence now that, and almost any formula that you would use on the left-hand side, there is an equivalent formula formed by the things on the right-hand side. This is why this whole business of rotation, there's not actually a whole lot extra to learn. I mean, there is content, but a lot of this is going to be rehashing in a new way how this rotational motion works, and we're going to see how it corresponds to linear motion or translational motion. By the way, I didn't quite define this, but translational motion is just the motion of an object moving. Linear motion is not quite the same, so I should be more specific and say translational motion all the time, because linear motion just means moving in lines, right? Whereas translational motion is just any general movement, but importantly, not rotation. Right, so there is one caveat here. There's a breakdown of this analogy between translational motion and rotational motion that's kind of buried in this formula, or in this correspondence here, right? So unlike mass, which you can just, like, the amount of mass you have doesn't change depending on where that mass is, right? If I put this pen here, it has the same amount of mass as if I put it here. It's not momentum. It's the equivalent, it's rotational mass is the best way to think of it. It is the thing that you would multiply by angular velocity to get angular momentum. And we'll get there. But it plays the role of mass. It's a scalar, just like mass is a scalar. But anyway, yeah, so if I take this mass, my pen, and move it over here, it has the same mass. But importantly, if you look at this formula that we had for rotational inertia, it not only depends on the mass of the object, it also depends on where that object is relative to some axis of rotation. So for example, two objects that might have equal mass, well, or they could have equal mass and they could have equal rotational speed, but they might have different rotational kinetic energy because that mass might be distributed in a different way. So let me, it's not really due to torque, and we'll get to torque as well, but I'm going to treat you guys like blank slates, so I promise we'll cover all of this, but I will explain where things come from, but it's not really due to torque, it's just due to the nature of how rotational motion works. So let me show you a quick demo. Unfortunately, I can't do it with my hands, but there is a YouTube video of kind of a silly sounding guy. So let me share another video or another window. So if this was a normal class, I would just show you because I would do the demo myself, but instead I have to deal with this silly guy, so I just Googled this. So what's going to happen here is, oh, okay, you're familiar with this guy? Oh, come on, pause. Pause. All right, so let me just back up, pause, give some intro, and then I'll explain what's happening. So I just need to, okay, so in this picture, yeah, I guess I actually have never heard of this guy before. It just popped up as the first thing I Googled, or I YouTubed anyway. So in this setup, there's two different systems. They both have the same mass. Notice that they both have the same central axis, and they both have these four masses on these rods extending out from the center, and they both have the same force being applied to them. They have the same weight attached, and it's attached to the edge of the central axis so that it applies a force to it. But the point here is that because the mass is distributed in different ways for these two setups, you would expect them to behave differently. And so we can see that here. So notice that the one on the left accelerates. I'll talk over him. The point is that the one on the left rotated significantly faster than the one on the right. And the reason for that is because the one on the right has all of the mass is at a further distance. So the contributing factor to moment of inertia is not just the mass, it's also this R factor. It tells you how far away you are from the axis of rotation. And if that R is larger, then the object behaves as if it has more mass when it comes to rotation. And things with more mass tend to be harder to get moving. So the one on the right, oh wait, you can't see what I'm pointing at. The one on the right behaves not as if it had more mass, because it doesn't have more mass, but it has more rotational inertia. So it's harder to get moving because the position of those masses is further away from its central axis. And so the idea here is, or the thing to grok, the thing to try to like kind of wrap your head around is things are harder to rotate if their mass is further away from the axis of rotation, i.e. they have more energy, like two things rotating at the same speed will have, let me rephrase, if you have two objects rotating at the same speed, but one has more of its, and they have the same mass, but one has more of its mass further away from the axis of rotation, the one with more of its mass further from its axis will have more rotational kinetic energy, because it's proportional to not just the mass, but it's also proportional to where that mass, or how far that mass is from its axis of rotation. Similarly, we're going to get to angular momentum later, but a thing with more mass, a thing with a larger moment of inertia, i.e. Its mass is further away from its axis of rotation, it will have more angular momentum at the same angular velocity. So that's going to be the one thing that kind of pops up again and again. Kwong, that's exactly why that happens. And actually, that's probably going to be on a homework assignment. The idea here is that if you bring your mass closer to the axis of rotation, if your angular momentum is going to stay the same because of conservation laws, then your velocity has to increase because your moment of inertia decreases. But again, we'll get to that later, but that's a really good insight. So the distinguishing feature between rotational motion and translational motion is that rotational motion also cares about where the mass is, not just how much you have. That is like the one distinguishing feature that throws people off pretty significantly. All right, so what we're about to do is something that I've discovered is probably the hardest part of the course. We have to do it. It's the part that people struggle with the most because it involves the most calculus. We're about to calculate center of mass. So center of mass is always center of mass, but it's not always straightforward to calculate, right? So let's talk about calculating the center of mass and rotational inertia, COM, and rotational inertia. I'm basically going to teach you how to calculate both of those things. So you already know how to calculate center of mass a little bit, right? You just add up the position vectors of each of the blocks, and then you multiply, or you add up m times r for each of the blocks, where m is the mass of the block, r is the position of the block, and then you divide by the total mass. But that doesn't work super well when you're talking about a rigid body, because a rigid body doesn't have individual blocks. It's like a continuous object, so we need to figure out a different way to do it. But importantly, note that both center of mass and rotational inertia, I'm just going to call it I, depend on the distribution of the mass, right? That's certainly true for center of mass. The center of mass, where the center of mass is, depends on where most of the mass is. And as I showed above, or as I hope I showed above, the moment of inertia also depends on where your mass is relative to some fixed axis. However, the difference is that center of mass is a vector, and rotational inertia is a scalar, right? It's just like how mass is a scalar, rotational inertia is a scalar. And just so I can be on the record as not lying to you, rotational inertia actually isn't a scalar. In fact, it's a tensor, but we're not going to talk about that this quarter. If you are a physics major, or if you take higher physics classes that will involve doing these sorts of things in detail, you'll learn about that later. But for our sake, it's a scalar. So let's figure out it's a tensor. A tensor is like a matrix that behaves a certain way. Don't worry about it though. Completely out of the scope of this course. Right, so we know how to calculate these things, both of these things now, hopefully, given like discrete lumps of stuff, right? So let's briefly go over that. For discrete lumps of stuff, the center of mass is, well, it's the mass of the first lump times its position vector plus the mass of the second lump times its position vector plus ... divided by the total mass, right? We already know how to do this, where each r sub I is displacement from the origin, or maybe from some point of axis on rotation or some reference point. Usually, when we're talking about center of mass with regards to rotation, it will be measured with the reference point being the axis of rotation. And so we can also do this for the moment of inertia. So I showed you basically how it's calculated. It's just the mass of the object times the distance that object is from the axis of rotation squared. So I is m1 times r1 squared plus m2 times r2 squared plus ... where each r sub I squared is the squared distance from the axis of rotation. And just to be on the extra safe side, remember that if I write something like r1 squared, what that really means is it's r1, the vector, dotted into itself, or equivalently, it's the square of the magnitude of the vector. So both of these formulas involve the same things. They both involve the masses of lumps of objects, and they both involve the displacement vectors of those objects. So the trouble is real life isn't that nice, where you just have lumps of things that behave as indivisible lumps. I.e., real life objects don't have a finite number of point masses. They have an infinite number of, it's like a continuously smooth object. So let's think back to calculus. So for real objects, oh, actually, before we continue for real objects, we can summarize this using calculus notation. RCM might be the sum from I equals 1 to n of m sub I, r sub I, the vector, divided by the sum from 1 to n of m sub I, and the moment of inertia would be the sum from I equals 1 to n of m sub I times r sub I squared, right? So now let's go back and think about real world objects. For real world objects, there's not a finite number of discrete things. Instead, it's continuous and smooth. So that means we take the limit as n goes to infinity. That's basically what you do, right? Instead of breaking it up into a whole bunch of finite chunks, we just break it up into an infinite number of infinitesimal chunks. And so what happens then is that anytime we have a sum of I from I equals 1 to n of, say, mi times stuff, what happens is that this becomes an integral of stuff integrated dm. The mi plays the role of the dm, and the stuff stays the same. Now, this isn't particularly helpful, though, because what does this mean? So I'm gonna work through a whole bunch of examples now that will hopefully clear up everything that I was just mentioning. So let's work some examples. So let's say a rod has a uniform distribution of mass, a uniform rod with a mass density which at least for a rod might be mass per unit length. So it's almost like just regular density, but it's per unit length because the distribution of mass in the other directions isn't relevant, of lambda. So we typically use lambda to refer to linear mass density, which is what we're talking about here. The thing to think about is, like, imagine that you had a block made out of a single object like copper. Copper has a specific density, and you could figure out what its total mass is by multiplying its volume by its density, right? But you could also describe the mass per unit length of the copper by taking its total mass and just dividing it by its length. And then every, say, centimeter of copper rod would have a certain amount of mass. And that's what this lambda tells you. It tells you what is the mass of a certain length of your rod. So if it would help, maybe imagine lambda has units of, or lambda is the value 5 grams per centimeter, for example. Like, it's just some number that you would either look up or you could calculate in various ways. And again, I'll go through examples so you'll be able to see what I'm doing. So if the rod has mass m, meaning maybe it has a mass of like 600 grams or something, and length L, the question is what is the mass density? Now, because I basically just told you how to do this, lambda, I basically just told you how to do this, but the question is how does the mass and the length and the mass density, how do they all relate to each other? So in this case, because the object is uniform, meaning that the mass doesn't change, or the density of the object doesn't change throughout, that means that that the mass density, as calculated by just dividing the mass by the length, should be the same as if you calculated it as dividing part of the mass by part of the length. So the question is how much mass is in a chunk of length L, is in A. That's a chunk of length L. And I'm going to use lowercase l here. So we know how much mass is in a chunk of length capital L. That's just all of the mass, right? So what is the mass of the, if let's say that L is, let's just use some real world examples just to ground us. Let's say L is 1 meter, mass is 600 grams. Then lambda is going to be, what, 0.6 grams or 0.6 kilograms per meter? So the question then is what's the mass of half a meter of this stuff, right? Well, you could just, I mean, it should be pretty obvious. It should be half a kilogram, or sorry, 0.3 kilograms per meter. But we can calculate this another way. The mass of some chunk of length L has, it should be proportional, or it should be proportional to the ratio of the length little l to capital L, i.e. it's just the total mass times the ratio of little l and capital L. And so we can rearrange this. This is just L times capital M over L, which is just lambda L, right? because lambda is capital M over L. So what is the mass of an infinitesimal chunk? Chunk of this rod? Well, we do the same thing. M is equal to lambda times the length. So in this case, the mass of the infinitesimal rod, we know it should be infinitesimal itself because an infinitesimal thing should have an infinitesimal mass. So we call it dm. dm is equal to lambda times dl, which is the infinitesimal length. And so I'm just going to draw a picture here so you can see what I'm referring to. Here's our rod. Maybe this is x equals 0 down here, and this is x equals L up here. If we want the mass of this tiny infinitesimal chunk, dm, well then, what do we calculate? Well, maybe this is at some position x. And so this length, this tiny infinitesimal length, that's dx, right? This length here would be dl. And so in our coordinate system, we would call that length dx. And so what we can do then is we just write that because we're using some sort of coordinate system, here we have x is up. This would just be lambda dx. And so just by rearranging this, we get that lambda is dm divided by dx, or it's the derivative of the total mass m with respect to x. So what this lambda really tells you, this is a definition by the way, what this lambda really tells you is, start at the bottom. How much mass do you gain per unit meter as you go up, right? So we could write the mass as the total mass underneath a certain point. We could write that as a function of x, right? So the total mass that I've shaded in would be m of x. And so then lambda is just the derivative of that mass function as a function of x. So that's what lambda is. Lambda tells you how much do you gain, how much mass do you gain as you inch up your rod. I know that this is a lot, and like I said, this is the trickiest part of the course, but we need to get through this because it's involved. I'm trying to go slow. If I'm going too fast, though, let me know. By the way, also, I'm going to be using symbols a lot, and that's just because I want you to get used to seeing the symbols that are associated with various quantities. But if you're stuck, just imagine that I replace all these symbols with numbers, and like it shouldn't be any trickier. All right, so let's continue. So how do we use this knowledge? How do we use this knowledge to do the integral? Right. So if we wanted to find the center of mass for this continuous object, because it's not just a whole bunch of chunks separately, we would need to do something like an integral of, well, center of mass is just, well, if we wanted to say find the total mass, the total mass is I equals 1 to n of m sub I for discrete, so that would become an integral over the whole rod of just dm, right? Because there is no stuff. Yeah, that's, since the rod is uniform, is dm dx a constant? Yes, Christian, dm dx is a constant in this case. And roll, yes, we are going to take an integral. So the question is how do you actually calculate that thing? We're probably going to go till 2:30. If you can't stick around, do watch the lecture. I'm sorry I have to do this, but we need to catch up. So how do we actually do this integral, right? Like, what does it mean to integrate not over a coordinate system anyway? Well, turns out that we can rewrite it in terms of a spatial integral. And that's what we're going to do in all of these cases. We're always going to rewrite these things as spatial integrals over some coordinate. So remember that dm is lambda dx by definition. And so what we get then is that the integral over the whole rod, dm is, well, okay, so what are the bounds? And so in terms of x, what are the bounds of the whole rod? Well, it's 0 to L. Those are the bounds of our whole rod. And then dm becomes lambda dx. And so this just becomes lambda L. And we know that because lambda is constant, this is a uniform rod, we know that this is equal to m over L times L, which is just m. So it checks out. We integrated this dm and we got the total mass. That's good. All right, what about the rest of the center of mass? So remember that we need to know the total mass to find which is the denominator of the center of mass. Now we need the top, which is the numerator of the center of mass. So xcm before would have looked something like sum equals from I to 1, from 1 to n of, say, mi xi. That's what the numerator would look like. And so this becomes an integral of x dm. And so what we have is we have the center of mass position is the integral of x dm divided by the integral of dm. And so now we can actually just do these replacements and transform them into spatial integrals. So x is just still x. It is the position. It is the x position of the small chunk of mass. So this small chunk of mass would have position x. And so it's just x times lambda dx. And the bounds are the same. It's the whole rod. And we just divide it by what we did before. And we already know that the denominator is the total mass. And so now we can just do the integral, right? This is x times a constant. So this just becomes lambda x squared over 2 times 1 over m evaluated from 0 to L, which is just lambda L squared divided by 2m. And remember that lambda is m over L. So this is 1 over m times m over L times L squared over 2, which is precisely L divided by 2. And so we find that the position in the x coordinate of the center of mass is L divided by 2, which is precisely in the middle. That's exactly where we expect it to be for a uniform rod, right? So this might be, let's call it L over 2. This is the center of mass, and it's in the x direction because this is a one-dimensional problem. Now, this was easy because the rod was uniform, but what if it's not uniform? Well, then things get a little bit trickier. But all of the techniques that we used above are still the exact same. So let's do another example. Let's say the rod is twice as dense at one end as it is on the other. Twice as dense on one end as the other. And the density changes linearly. So the idea here is like, imagine like a constant gradient of material. So you have like something that has one density, it's the object is 100% that object on one side, and then another material that's twice as dense, it's 100% that twice as dense material on the other side, and then it's a gradient between the two that's like a constant gradient. So so think like, I'll draw the rod again. Let's say we have x equals 0 here. We have like a light material here, but it gets denser as you go up, and it gets denser and denser but it gets denser at a linear rate. So let's call the density at the light end, or this is the linear mass density. Density at light end, let's call it lambda naught, just because. So we need a linear function. We need lambda as a function of x, because we need to know what the density is at different places along the rod. So we need lambda x such that lambda of 0 is lambda naught. We also know that lambda of L is twice as dense, so it's 2 times lambda naught. And we also know that lambda of x should be linear. It's mx plus b, has some formula like that. So in this case, we have two equations that two equations that we can use. We have two variables, m and b. And so we can just solve explicitly. Just plug in x equals 0, x equals L. Those are two different equations. And then we just solve for m and b. And so I'm not going to step you through the process, but it should be fairly easy to see why this is true. It turns out that you get that lambda of x for this example is x plus, or x divided by L plus 1 times lambda naught. One way to see this is if you plug in x equals 0, you get 1 times lambda naught. If you plug in x equals L, you get 1 plus 1 or 2 times lambda naught. So it checks out. So that's what our linear mass density is. And in this case, it changes with time. And that is all to say, as you step up the rod, the amount of mass that you gain as you go higher and higher increases at a faster rate because the density is changing. So every small chunk has an ever increasing mass as you go higher and higher. So now that we have this, remember, you basically always need the linear mass density function because that describes how the mass is distributed in your rod. Now we can use that to find the center of mass. So the center of mass certainly should not be in the middle here, right? Come on. Scroll for me. There we go. It certainly should not be in the middle because if we were to break it in the middle, the center of mass is basically the line that you should draw that has the same amount of mass on either side, right? So if it were in the middle, but the top half is more dense than the bottom half, then you'd have more mass on the top half. So it can't be in the middle, it has to be somewhere else. And in fact, we can explicitly calculate it using the tools above. So the x center of mass, well, that's equal to 1 divided by m, where m is the total mass, times the integral along the rod of x times dm, just as before. That's the formula for the center of mass position in the x direction. So in this case, what is dm? Now, again, we have a formula for that. dm tells you how much mass a little chunk of length x has, or length L. And so it turns out, or conveniently, dm is always lambda dx, or lambda dl rather. Yeah, it's always lambda dl, but and then we write that dl is dx because we use a coordinate system. So in our case, dm is now lambda dx because we're using an x coordinate. So then the x center of mass position is, well, it's 1 over m times the integral over the whole rod. So the rod extends from 0 to capital L, as usual. And then it's x times lambda of x dx, right? Because this is, rather than being a constant, this is a function now that we have to integrate. But it's not a hard function to integrate. This is x times something that's linear in x. So it's just lambda naught divided by m times the integral from 0 to L of x over L plus 1 times x dx. And now it's just an integral. Now you guys can just do this. Just to save time, and you guys know how to do quadratic integrals, it works out that you get 5/6 lambda naught L squared over m. And that should be kind of believable. You might expect that it would be L cubed, but there's this factor of 1 over L here that's going to cancel one of them. So that's what you get. And you could even check the units. Lambda has units of kilograms per meter. L has units of meters. M has units of kilograms. So kilograms per meter times meters squared divided by kilograms. That's just equal to meters. And the center of mass, the center of mass position should be a distance, right? It's a position. But we're not quite done because this doesn't tell us actually where it is because it depends on lambda naught. We want it to be in terms of like L, we want it to be 1/3 of the way up, like L over 3 or 2L over 3 or something. So how do you get rid of lambda naught? Well, we have another equation that we haven't used. Remember that the total mass is just the integral of the whole rod of just dm. You just add up all the little chunks of mass. And so that's the integral from 0 to L of lambda of x dx. And so again, this is an integral. It's just lambda naught times the integral from 0 to L of x over L plus 1 dx. And then some ... And you get that this is equal to 3/2 times lambda naught L. And so what we can do is we could solve for lambda naught in terms of capital M and L. So that gives us is 2/3 M over L. And so therefore, the center of mass position, well, now we just go back and we plug this lambda naught back in there. And so we find that this is 5/6 lambda naught L squared over M, which is 5/6 times 2/3 M over L, L squared over M, and that's just 5L over 9. Right, so this is our center of mass position. So if we go back and we look up at our rod, we find that the center of mass position is slightly higher than the midpoint. The midpoint would be like 4.5 L, right? This is, or would be 4.5 L over 9. Ours is 5 L over 9. And that makes sense because the mass is more dense up top than it is on the bottom. So it makes sense that you would need to have more of the bottom part, because it's less dense there, to exactly cancel out all of, or less of the top part. And so this tells you precisely where that point is, where the mass above it is equal to the mass below it. All right, so we're going to continue doing examples because I know that that's important for you guys to learn. And I haven't actually computed rotational inertia at all either. So let's use these examples and compute rotational inertia. And by the way, the whole thing about computing rotational inertia, it's basically going to be the same. And the reason for that is, like, the only thing that's changing is that to compute the center of mass, we had to do x times dm. For rotational inertia, it'll just be x squared times dm. So again, let's start with a uniform rod. Uniform rod rotating about the about x equals 0, say. So the pivot point would be like here. And so it's going to rotate around. And so we want to compute the moment of inertia relative to that pivot point. So draw a picture again as a reference. Here's our pivot. It's at x equals 0. Here we have x equals L. And so we're going to compute basically how much effort would it take to get this rotating in the plane. That's what moment of inertia basically tells you, how much effort. So moment of inertia, I, is an integral over the whole rod, because it would have been a sum, but we're now integrating. And now it's just r squared times dm, where r is the distance of the mass dm from the pivot. It's like the actual distance. So the question then is how far is a chunk of mass dm at position x from the pivot? So we're considering this chunk which has mass dm and is at position x. Well, r equals x. It is x units away. Oh, that's weird. All right, I'll try to do that less then. Thanks for mentioning that, because I had no idea that it does that. Like, it's lagging like right now when I'm rotating, Well, I'll try to minimize how much I have to go up. I'll try to maybe I'll just like redraw things or rewrite things if I need it. But thanks for pointing that out. Right, so in this case, the distance that a mass dm is from the pivot is just its x coordinate. Now if I just dropped my pen. If I put the pivot instead, say here, at some other position, maybe x naught, then the distance would be x minus x naught. Or in fact, it'd be the absolute value of those things. Right, because the distance changes depending on where your pivot is. But in this simple case, the distance is just the x coordinate. So then, so further, dm is just lambda dx as before. And so what we get is that this is an integral over the whole rod, so it's an integral from 0 to L. This is just r squared, and r in this case is x. So this is x squared times lambda dx. So this is just lambda L cubed over 3, just doing the integral, and lambda was m over L for a uniform rod, times L cubed over 3. So this is mL squared divided by 3. So this is the moment of inertia about one end of a uniform rod. So remember, unlike for mass, where you can just tell me what is the mass of an object, for moment of inertia, it also depends on where the pivot point is. It depends on where your mass is relative to your pivot point. So when you specify a moment of inertia, you have to not only specify what you're talking about, you have to specify the axis that that thing might rotate about as well. And so that's important, because if I'd chosen a different place, it would have had a different moment of inertia about that place. So let's do this for a non-uniform rod. The same non-uniform rod as above. So just as before, we have lambda of x is x over L plus 1 times lambda naught, and we have that lambda naught is equal to 2/3 m over L. We calculated that above. And so if we are rotating it at about the same place, say the bottom, then the formula is the same. It's still r squared dm, and this is therefore an integral from 0 to L of x squared. In this case, now it's times 2/3 m over L times, now I'm just plugging in lambda dx. So this is r squared. And then this is x over L plus 1 dx. This whole thing is dm, which is equal to lambda of x dx. So now, but now this is just an integral. I mean, it's not a pleasant integral to do. You know, it's a cubic and a quadratic, but I trust that you guys can do it. I'm not gonna spend time doing the integral, but it works out that you get 7 over 18 ml squared. And so the takeaway here is that this is greater than above, i.e. before it was like 1/3 times ml squared. Here, 1/3 ml squared would be 6/18 ml squared. This is 7/18 ml squared. And it's greater than above because you have more mass further, I'm not supposed to be scrolling, sorry. More of your mass is further from the pivot point. And that's what affects the moment of inertia. It's where the mass is relative to the pivot point. Let's see if we can. All right, so I'm just gonna go, where did I get the lambda naught? Oh, this thing? So I calculated that above. I'm gonna scroll up, sorry, it's slow. But I calculated that above. We were doing the same problem. This is the same rod. So we calculated that by computing by setting the total mass m equal to the integral of dm. And so then and because the integral of dm has a lambda naught in it, then you can solve for the lambda naught in terms of m and other variables. I hope that answers your question. This is C above. Yeah, you could choose any pivot point you want. It doesn't even actually have to be on the rod. You could have chosen a pivot point over here, and then the distance would have been different because now you'd have to use like the Pythagorean theorem. You can choose any pivot point you want anytime. It's just sometimes it's more useful to compute a pivot point about a particular axis. And actually, that is a very good segue because now I'm going to go over something called principal axes. And I think this is going to be the place where I stop today. I'm going to finish with this. So real objects are three-dimensional, right? So before we were talking about discrete objects, now we're talking about real physical objects that are continuous and smooth, but they're also three-dimensional in real life. So they have three independent axes of rotation, or axes of possible rotation. The idea is, take my phone, for example. It could rotate this way, it could rotate this way, or it could rotate this way. 3 axes, right? Usually you can determine those axes by a symmetry. And each of those axes is going to have its own moment of inertia. Now, you don't have to choose the same 3 axes as everyone else, but sometimes it's useful to have a convention that we do use. Not momentum, moment of inertia, right? Because the axis that you choose to pivot around depends on the where your axis is. And by the way, let me just draw a quick picture. Let's say you have some object that's like extended, like it's a stake, and then you have some axis through it that it's rotating about, the point that you're calculating distance to is the point that it's closest to. So you wouldn't calculate distance to there. You would calculate distance to you would calculate the distance between the point on the object to the point that is closest to it on the axis. It's this perpendicular distance idea. But I'll talk about that more in detail later. So they all have their own moment of inertia for each axis. And those axes, those three independent axes, are called principal axes. And you're usually going to have one for the x, y, and z direction. They are the principal axes. Let's put an underline under that too. And a special feature of this is that, they intersect all three axes at the center of mass. And so that's what fixes these principal axes. You have one in each special direction, x, y, or z, and then they all come together at the center of mass. So what we do is basically we choose the we choose our axes, our principal axes, such that they are the x, y, and z axis if the origin is at the center of mass of our object. So for example, let's draw a sphere, or let's not draw a sphere. Let's draw a potato. Let's say it, and let's say its center of mass is here. It's somewhere inside. This is supposed to be a three-dimensional potato. Three-dimensional. Let's say the center of mass is here. Then what we do is our principal axes are these axes. So this would be one principal axis. This would be another principal axis. And this would be the third principal axis. And maybe the orientation's wrong, but the principal axes always pass through the center of mass. So the question is why do we put the principal axes at the center of mass? And so the axes have to be orthogonal to each other. Yes, they do have to be orthogonal to each other. But they could have been rotated, right? So the orientation is a little bit up for grabs. And this is going to be on the homework, but I'll give you a little bit of a discussion here. Imagine that you just have like a potato floating in space, right? And it's just rotating however which way. So the only thing, assuming there are no external forces on it, nothing pushing or whatever, the only thing that stays in a fixed place is its center of mass. It'll rotate freely and it'll do all its thing and just rotate in some direction, but its center of mass won't move. Its center of mass won't be going in a circle. So, so the idea here is that we want to choose the point of intersection of our principal axes as the point that remains fixed if there are no external forces. And that's just because it's the most, it makes our calculations the easiest. We didn't have to do that, but it's an easy choice. So I'm going to, I think I'll call it there. This whole business of the freely rotating body, on the homework, I'm thinking that I'm gonna ask you something. How do you know that the center of mass remains fixed? So I'll leave you with that, but think about it a bit. So I'm gonna stop recording there. I'm sorry that we had to go so much over.